the more difficult things I am. Is that a good or bad thing?
Good.
Actually,
All right.
I have no comment on this one.
Well, yeah, we have to get the class started. Okay. So let's go ahead and get started. So we are continuing our graph theory topic. And what we'll do today is to go over graph traversal and searching algorithms. And if we have enough time, we'll also go to mastermind as an example. Okay, that's going to be a fun one because how many people know how to play that game, mastermind, the board game? No. Okay, it's actually a pretty good one because I think it relates to both graph theory and also cryptography to a certain extent. Okay, not entirely, but to a certain extent, it also applies to cryptography. So we'll go ahead and get started with a graph traversal and searching algorithm first. Okay, so let's go here, and this is a really kind of long, boring kind of description here. So what I'll do is I'm going to, but there are hyperlinks. Okay, there are a lot of hyperlinks to Wikipedia pages and whatnot. So that's going to be the fun part. I'm just going to read the paragraph a little bit, sentence by sentence, but then I'll also go off the sentences and actually go to certain other pages to show you, what an algorithm may look like and what we are actually doing with these algorithms. Okay, so at this point we have the theoretical understanding of what is a graph. Okay, a graph is basically a tuple, a two-tuple. The first one is a set of all vertices, and then the second one would be a set of all edges. Okay, and at this point, I'm more interested in graphs that are directional than ones that are not directional. A directional graph is also called a digraph, D-I-G-R-A-P-H. It's basically directional graph in short. Okay? But a digraph is more interesting because a lot of problems are only going in one direction. Okay, you take an action, it will take you from one vertex to another vertex. So the question now is, why is it important to know how to traverse and how to search in a graph? Well, that's because most of the time, that's what we want to do. Okay, one way to look at a graph, okay, and this is the kind of graph that we see all day long, is to go to Google Maps. Okay, so when you go to Google Maps, I think this is the left where we left off from last time. So when you go to a particular place, and where is it? I think it's right here. Okay, so when you look at downtown Sacramento, which is what is being displayed here, this can be considered as a graph, where every intersection can be considered as a vertex, and then every segment of road to connect from one intersection to another intersection can be considered an edge. So if you look at this as a graph, why do you want to know how to traverse or how to search in this particular graph? What are you searching for, by the way?
How to get from point A to point B.
How to go from point A to point B. In other words, you're not searching for the destination. You already know where you want to go. What you are really searching for is what is the best way to go from point A to point B. Not just any way, but what is the best way to go from point A to point B. In other words, if I'm already here, okay, I'm just going to point on the map here. If I'm already here and I want to get over to here, obviously there's a pretty easy path here. There are multiple easy paths in this case. But I could also take from this point, go all the way onto the highway, go all the way to the East Coast, down to Florida, back to the West Coast, back up again in order to end up here. That is a path. No one says I cannot do that. It will just take me, what, a few weeks to do it? Okay, instead of just walk over in about half an hour, 15 minutes. I can take a few weeks and take a leave, to get it done. Okay? So the interest is not how to get there, it is what is the best way to get there. Okay, so typically we have a cost associated with each edge. So when you add up all the edges in a path, it becomes the cost of getting from one point of a graph to another point of the graph. One point being a vertex. Yep.
So are costs just arbitrary values, or just like one, for instance?
In this particular case, let me just kind of zoom in here. So if you look at this, if we just kind of consider this point, okay, from this point to this point here, the cost can be a combination of things, but when you're walking, it's probably just distance or effort, okay, how exhausted you will be by the time you get to the destination. But sometimes it's not the same thing as distance. In other words, there are cases where the distance is longer, but you may not arrive as exhausted, okay, because you may go uphill and downhill. San Francisco is one of those places where the shortest path is not necessarily the easiest path, because it might have a steep uphill and a steep downhill, as opposed to walking around on flat ground. Yep, go ahead.
Well, I mean, in this particular case, what you assign time would probably
Time would be a good one. A lot of times people are would consider time.
because you can make an average of the time it takes to travel
Yes.
each path based
Yes.
upon the speed limit of each road.
And also, intersections, the
yeah.
probability of hitting a red light and stuff like that. Google Maps, I think, take into consideration of a lot of those things, like speed limits and also traffic information, live traffic information. So it will take those into consideration. So when you use Google Maps to try to navigate from one point to another point, especially through downtown, the recommended path or the recommended route will differ, depends on what time of the day it is. Okay, so in the morning, when everybody's rushing to work and stuff like that, it will recommend a path that is going to be different from, let's say, midnight, where there's nobody on the street. Okay. The other thing that's kind of interesting, this just pops up in my mind. That's just how it works. This just pops up in my mind is Mythbusters. Okay, in one of the episodes of Mythbusters, they were looking into, is making several right turns really less, is it going to be more efficient than making left turns in San Francisco? Do you guys remember that episode?
Yeah, it's
No?
the myth
Okay.
about UPS drivers only make right-hand turns, and all their routes are designed so that they only have to make right-hand turns because it's
Yep.
the most efficient for gas.
Exactly. So it was actually, an interesting result, because the result was if you drive a normal, car, you're not saving a whole lot of fuel. Okay. But on the other hand, if you drive one of those, big brown trucks, or something like a big brown truck, the cost is actually significant. So the reason has to do with with a normal car, when you idle, your engine does not really consume a whole lot of fuel compared to when you're actually driving and traveling. But when you drive a big brown truck or anything like that, idling actually takes up a lot of gas. Okay, it takes a lot of fuel, when the truck is just sitting there doing nothing. So when you make right turns for whatever reason, you can actually save fuel even though you're circling around the block instead of making a left turn, because you're just idling, you're waiting for the left turn. And if you want to look it up, you can probably look it up pretty easily. So just say Mythbuster left turn. I think that should be enough. Yep, there we go. Right turn only mini myth. So you can look into, I think this one is probably the one that will, that has the whole thing. But that's, the kind of thing that you have to think about when you are traversing a graph. But in order to take left turn versus right turn into consideration, that means the vertices are not really just representing the locations, but they're also representing, which lane you're on, with that road, and a lot more information than just, okay, you're at this intersection, but there's more to it. Are there any questions about graph traversal? For those of you who have driven, who have the privilege of driving in San Francisco, do you think a digraph is more appropriate, or do you think a general graph where edges are bidirectional is more appropriate? That's a loaded question, by the way. Nobody has driven in San Francisco? Really? They have a lot of one-way streets, okay? So when you have a lot of one-way streets, what kind of graph are we dealing with? A digraph or a bidirectional edge type of graph? A digraph for sure, right? Because you can only go in one way. Now you can look at it as a bidirectional edge too, but the cost of going in one way is a lot more expensive than going the opposite way because the cops will slow you down by giving you a ticket, and obviously there's a monetary cost to it as well. Okay, when you're going in the wrong way in San Francisco, when you get into a collision, that even bumps up the cost even more. So there's always a way to look at, hey, that's an edge going backwards too, but it's so expensive that you're not going to take it. Okay, is it okay so far with a graph traversal? Why we need to do it? Okay. So getting back to my own notes here. So in a graph that is representing a game of chess, okay. So what we're dealing with here in this case, when we are searching through this graph, is we are searching for a way to win the game with minimal risk. Okay. There are multiple ways to win a game, to win a match of chess, okay? And there's a shortest path too. But the shortest path will probably be making assumptions about your opponent not doing much to resist you, okay? That may not be the best assumption. So in a game like this, where you have an adversarial player, there are special techniques when we do these kind of search. It's called alpha-beta pruning. And there's one entire branch of AI or artificial intelligence dedicated to playing games where you have an adversarial player. You can look it up. It's simply called game theory in computer science. So if you look up computer science game theory, right there. Okay, game theory is the study of strategic decision making. Specifically, it is the study of mathematical model of conflict and cooperation between intelligent, rational decision makers. And in a board game, like a game of chess, it falls into this category. Is that okay so far? And there are special techniques for game theory that I'm not going to talk about in this class. But I will give you the name of one of these techniques. It's called alpha-beta pruning. Alpha-beta pruning, which has its own page because it is a fairly well-studied type of technique. The basic idea of alpha-beta pruning is out of the entire graph, you can prune off an entire chunk of it just by saying, oh, up to this point, the cost of this vertex is already more than the alternative path that I have explored. So there's no need to explore this chunk of the graph anymore because none of these vertices can be less expensive compared to the one that I have already traveled. But the alpha-beta part has to do with you minimize, with certain nodes, with one layer of nodes, and then you maximize with the next one. Because you minimize when you are playing, when you're thinking of what your opponent would do, and you're maximizing when you are playing, or when you are simulating what your move is. So you have to minimize with one, maximize with the other one, minimize with the next one, and maximize with the other one. And that leads to a special technique to make the search a lot faster. It's called alpha-beta pruning. I'm not going to talk about alpha-beta pruning technique in this class because we are only going to talk about graph theory in general, but not in specific algorithms. Are we doing okay so far with all the topics up to this point? Okay. So getting back to my text here. Yep.
Is that specifically for, is that like a category under game theory?
Yes, it is. Alpha-beta is a special technique under game theory. And game theory can be considered as a branch of graph theory where you are specifically interested in graphs that represent how adversarial players interact with each other. And for those people who are thinking, I really don't want to know any of this, because I just want to write video games. Well, guess what? It is related to video games. How is it related to video games?
Well, game theory, right? Yeah. I mean,
Well,
you
it
play
is
against
called game
adversaries.
theory, but the game theory applies to people playing against people, right?
Yeah.
But why would it be related to video games? When was the last time you played a video game that is both network capable, where you can play with other players, or you can play, just with the computer, and you're bored with playing with the computer within like half an hour? It's like, okay, I know how to beat up the computer already, consistently and predictably. So I just want to find some other players to play with. That happens all the time, right? Because the AI of most games are not exactly very smart. Okay, they may have super duper response time, and they can cheat as well. Okay, when you're thinking about games like StarCraft, okay, if the computer cheats, they know exactly where you are, they know what you're developing, what technology you have, and they can just spend all the minerals and all the gas in StarCraft, and they can spend all the resources just to develop technology to counter yours, and not really to follow a particular route to do it. So they can cheat, but if the computer only has as much information as a normal player has, the computer usually cannot make decisions as optimally as a person, okay, or cannot respond to your strategy as flexibly as a person would. Does that make any sense? So that means if your interest is writing video games, this can be useful too, because it can help you develop video games that have better AI and make the game experience more satisfying to people who are looking for a challenge. Instead of, oh, okay, I can finish this game in half an hour and I'm just trying to bump up my highest score, right? It would be kind of fun to have a game where the AI would actually learn from you. So the more you play with the game, in that game, the more experienced the computer becomes, and the harder it gets to actually finish the game. That would be a kind of the game that would be interesting. Are there any video games like that out there? No. Well, there you go. Here's your idea of becoming the next billionaire. So you can sell your company and start off other companies like space exploration, electric cars and stuff like that. You guys know who I'm talking about?
Elon Musk.
Yep, Elon Musk. Yep. All right.
He's like the real life Tony Stark, if there ever was one.
He is currently my best role model, I think. Yeah, people keep talking about Bill Gates or Steve Jobs. Neither of those fall even close to what I would think as a role model. Elon Musk, is closest to what I think would be a role model. Any questions at this point? Who's Elon Musk?
SpaceX,
Really?
Tesla.
You guys don't know?
SpaceX, Tesla,
PayPal.
PayPal.
It all started off with PayPal. The guy who started off PayPal, he sold PayPal for what, $1.something billion, which is not a
co-founder. He and another person.
Yeah, but he sold all his share. I
Yeah,
think.
he sold his shares off for a couple billion or so, and now he's an angel investor, pretty much.
Elon Musk. The name is South African, so that's why it's not doesn't seem English to us.
He's rich and he's pretty.
He's Canadian. He's Canadian American entrepreneur, but I think his family came from South Africa. And if you look up his entries, this is the guy, and he talks like an engineer too. The latest thing about him, if you guys have not been watching, is he's trying to land the first stage of a rocket on is it 100 meter by 100 meter platform on a barge in the ocean. Okay. Think about all the classic footage of rockets being launched into outer space. Okay. The first stage rocket is the big chunk of item, the bottom part of a rocket, and it propels the rocket up to a certain point, and then what happens to the first stage rocket? The fuel gets used up and becomes dead weight. It gets detached from the rest of the rocket, and then what happens to it? It just falls back onto the Earth, and it's done, right? I mean, it cannot be reused. As it turns out, the first stage rocket on most rockets is the most expensive part. Okay, and to be able to reuse the first stage rocket, should have been the priority. Okay, instead of focusing on the vehicle itself, like a space shuttle, they should have focused on the first stage of a rocket. But nobody has ever attempted to make a first stage rocket land itself on a platform so it can be used again. So initially, the Elon Musk contacted, I think, the Air Force of the United States and say, well, I might be able to do this, so, I want you guys to kind of either fund him or, maybe not. Maybe he's entirely self-funded with these projects.
Self-funded and other angel investors.
Yeah. But the Air Force, had a really big goal. It's like, I'll give you a 1 km by 1 km, 1 kilometer square, and if you can do it, we'll consider using your technology. And Elon Musk look at their criteria and go like, no, we're not going to do that. We're going to do 100 meter by 100 meter, not 1 kilometer by 1 kilometer.
They tried that and it failed.
The Air Force?
No.
Elon Musk?
Yeah, SpaceX.
Well, he tried it several times already, but each time it's getting closer to actually getting done.
They had a launch like a week ago, and they tried landing it on
Yep.
the ocean, and it blew up.
Yeah, but it got pretty close, and Elon Musk feedback, in a news conference was really technical. He actually named the component on the first stage rocket and say, "Oh, it's probably because of blah 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 blah. It should be easy to fix." That was his comment. It should be easy to fix.
You man crushing on Elon Musk.
Well, there were a few things. I think in one of the attempts they ran out of hydraulic fluid. Because on a rocket like this, it's not a closed loop. So hydraulic fluid only goes in one way, and once it is spent, it is gone. And so in one of the attempts, I think he ran out of hydraulic fluid. So when you run out of hydraulic fluid, you can no longer control the fins and the thrust, and so it just kind of like that.
You actually find the latest landing and music.
Oh, there are tons of them. And then in one of the attempts, I think he almost landed, but the sea was rough on that day. And as a result, it just kind of it failed in that particular attempt. But it's getting closer. Okay, this is something that nobody else has actually attempted. Elon Musk is also the owner or the founder of Tesla. Okay, I'm pretty sure most of you have heard of Tesla, right? Okay.
There's a lot of stuff about him. I mean, the Nikola Tesla Museum in New York, they actually, by donation through him, were able to meet their goal of $1 million to buy back the property. And then he decided to donate a supercharger station for Tesla Motors cars, like the Tesla Model S. It's $750,000. He basically donated $2 million of his money to that too. I mean, he's a cool guy.
Yep.
And pretty.
So I'm just saying that some of you may be the next Elon Musk. Instead of the next Bill Gates or the next Steve Jobs, be the next Elon Musk. Yep.
I heard some of his early prototypes of the rockets. He was looking at he was in talks with Russia about buying like a Russian ICBM just as an initial prototype for his rockets. So you could buy a Russian ICBM.
Off of an auction or something.
I actually don't know where, but I think he was in talks with somebody to buy one.
eBay.
But he decided against it because it was too expensive.
Yeah. All right. Well, so getting back on track here. That's the hard part of this class. If a graph represents delivery points of a delivery truck, a search can be used to find the least expensive way to deliver all items. Do you think this is important to UPS, or do you think UPS looks at this and like, oh, that's all gadgety thing. We don't really care about algorithms or anything like that. Do you think it is important to UPS? Do you think it actually saves money when they use a computer to plan the truck routes?
Sure they do.
Tremendously, okay? Tremendously, okay? This is actually big money for not only UPS, but also for trucking companies, any commercial entity that has to deliver stuff. This is actually a big deal. Yep.
I have a comment about that. My brother drives a truck for a living, and the GPS that he has actually has routing software to make it the least expensive ticket somewhere.
Well, it makes use of a certain heuristic, so it will give you a pretty close to optimal path, but sometimes, between the most optimal and the second most optimal path, the difference is negligible. I mean, it's just because, you miss one light, it will bump you one route to the next, optimal. Okay, so what we want to do is also talk about state space search, okay, where a vertex of a graph represents a certain state, such as the board configuration of a chess game or mastermind or something like that. Okay, so in those cases, an edge is going to represent an action and therefore a transition to another state. So you start off with a particular known state of a chessboard, and then you say, I'm going to make this move. That move is an edge to take you out of the initial state or the state where you are in and lead you to the next state because things have changed. Okay, chess pieces have been taken or at least been moved. Okay, so that's how a state space is really looked at. It's just a graph where each vertex is a particular state of the system. And in these situations, a search algorithm to go through a state space, and typically they want to go from a initial state to reach one of the final states and figure out what is the easiest way to go there or the cheapest way to get there. These algorithms in general are called state space search algorithms. It's a big category of search algorithms because it's used heavily in AI or artificial intelligence, and it is really just in general useful. And we'll talk about several of these right next to this paragraph. The classic state space search algorithm is known as Dijkstras algorithm, and it's a funny name because it is not English either. Dijkstra is invented by Edgar W. Dijkstra in 1956. So this is a pretty early algorithm, and this particular algorithm, if you just kind of read the first paragraph, that's what it says. Dijkstra's algorithm is an algorithm for finding the shortest path between nodes in a graph. A node is the same thing as a vertex in this class. Okay, so we're talking about finding the shortest path between two vertices in a graph, which may represent, for instance, road network. It was conceived by computer scientist Edgar W. Dijkstra in 1956 and published 3 years later. I think that is shortly after Alan Turing committed suicide, or at least allegedly committed suicide, but he died. Okay. The algorithm exists in many variants. Dijkstra's original variant found the shortest path between two nodes, but a more common variant fixes a single node as the source and finds shortest path from the source to all other nodes in the graph, producing a shortest path tree. So we're not going to talk about the details of this algorithm, and for those of you who are interested, you can definitely
Taking up your vision math class?
well, no, this is more of an algorithm thing. You can actually implement this algorithm. And there are alternatives to this algorithm. We'll talk about A*. I'm just kind of curious of whether B* is the one that I have been searching for. Best first graph search algorithm. Okay, I'm just taking a quick peek here at the algorithm. Does it describe? No, it does not. Okay, never mind. Okay. So this is my paragraph of what it does. So the rest of this is really kind of boring, okay, except for this one here. If you want to understand how the algorithm works, this is how it works. So it's best to visualize this algorithm as a maze where you have stationary but initially live cockroaches. The starting point is where you will inject pesticide. And the order of how the cockroaches will die in the maze is basically showing you the shortest path to each cockroach in the maze. Okay, nobody seemed to be interested in cockroaches or pesticides? No? Okay. So the way you can kind of visualize this is you can imagine it as a maze. Okay, I'll just give you a very simple one. And okay, it's a 3x3 maze. It is a square maze, and so you can kind of imagine that you have a whole bunch of cockroaches here. So each cell has one cockroach. All right, and you want to designate one of the cells as the origin. Okay, this is where you start. Okay, So I will just say that the center cell is my origin. This is where we start. Okay. And I put a 0 here because the time delay between the time I start to spray pesticide and this particular cockroach dying is going to be 0. It is at ground, is on ground 0. Is that making any sense? So which 2 cockroaches will die next? The neighboring cockroaches, right? What about this guy? Not yet, right? Because there's a wall here that is fending off the pesticide. So the next one to die would be these 2. So I put a 1 next to it because it is at 1 unit of time delay from time 0. Is that okay? This is going to be 2. This is going to be 2, 3, 4, 5, 6. Guess what these numbers are? They are the cost, okay, to get to each node or each cell in this particular 2-dimensional maze. Okay, that's basically how Dijkstras algorithm works. Okay, it's called the breadth first search algorithm because it expands the perimeter of, in this case, the pesticide, and it wants to find out which cockroaches are currently on the perimeter of the spreading of the pesticide. And that's why that's how it works. So if you're only interested in a particular cockroach, like this one here, then it will cost you 4 units of time to go from here through the shortest route to that particular cockroach. Now you can kind of imagine when this maze gets more complicated, where you can have loops and stuff like that, it gets a little bit more complicated. But you're still analyzing how quickly you can spread the pesticide to each individual cell, because loops really does not matter. Okay, if one cockroach is dead already, it doesn't matter that it has a loop from another path, because you're just calculating the time, when a particular cockroach will die, because it's not going to die again. These are not zombie cockroaches, so we are not going to resurrect cockroaches to let them die again. Which makes finding the shortest path a lot easier. If cockroaches can be like zombies and they just become undead, that becomes a more tough problem. Some of you may actually write a dissertation in your computer science PhD to say, what if cockroaches are zombies and they can come back to life at least 4 times? What would be the quickest way to kill a cockroach 4 times in a maze? And what is the algorithm to do it? So jot it down, for those of you who want to go to graduate school, jot it down, just say, maybe this will become a good dissertation. It will become a good dissertation if you can map the zombie cockroach problem to a real life problem. Okay. Sometimes we look at these problems and go like, oh, that's kind of funny, but then you can map it to a real life problem, then it becomes actually practical and useful. Are there any questions about the cockroach problem, which is kind of visualizing Dijkstras algorithm? No questions? Okay. Does anyone go to picnic day, like I would say at least 5 years ago? Do you know what is micro mouse competition? No? Okay. So what I'll do is I'm just going to digress one more time, okay, to talk about what is a micro mouse competition. Micro mouse competition. So there you go. Well, it is important enough that Google has an instant display of the content from the wiki page. A new version of micro mouse is called a half-size micro mouse competition. So if you go to the wiki page, this is typically how it looks like. This may even be a UC Davis maze. It looks like one, but it may not be. But never mind. So basically the problem, this is usually considered a senior year engineering project class. So for a lot of UCs and CSUs, well, some, I shouldn't say a lot, but for some CSUs and UCs, this is one of the classes that students have to take in the 5th year as an electrical engineer, or a computer engineer, where they will have to construct a robot, okay? Kind of like the one, on the screen here. This is not typical. This one is actually a lot more refined compared to the typical robot. But basically what you do is you program this robot so it's fully autonomous. There's no communication between you and the robot. You put it, there's a certain starting point in the entire maze, and this would serve as a good starting point. The objective of the robot is to get to the center of the entire maze as quickly as possible. Okay? And which robot wins is determined by how much time it takes to go from what we call the origin, starting cell, to the center of the entire maze. Is that okay? And the robot is allowed time to do exploration, okay? And it does not know the configuration of the maze to begin with. In other words, when you first put the robot into the maze, it does not know how the walls are all configured, okay? In other words, it now has two problems to solve. The first one is to figure out the configuration of the maze, and number two is to try to get to the destination as quickly as possible. And it is allowed to traverse the maze as many times as it needs in about 10 minutes of time or so. Okay? How would this be related to the stuff that we have been talking about today?
A lot of the graph theory stuff would have to be used because the robot would have to construct a grid within its own memory to know where it's going, where it is, and what is possibly still left to explore.
Okay, and the big question is, of the portion of the maze that has not been explored, is it even possible that a shorter path exists in that region? Because if you know that the region that has not been explored cannot possibly contain a shorter path, why even bother with it? Does it make sense? Okay, and the flood field algorithm, which is commonly used in the micro mouse competition, is a modified version of Dijkstras algorithm. It is completely specialized to deal with a two-dimensional maze type of problem, but the approach is the same. It is a breadth-first search algorithm to locate the destination. Okay? So this is an actual practical application of graph theory and search algorithms. Okay? And in order to implement such a search algorithm, what type of computation power do you think we are talking about here? Remember, these things do have to run in real time, okay? You cannot just say, okay, I'm gonna spend about 5 minutes just sitting here to recompute all the values to find the shortest path. These things move constantly. Let me show you a video showing you, these micro mice in action.
Well, I mean,
let's see.
Processors are available pretty small now.
They are.
Do they ever crash into the walls?
Oh, all the time. Are you kidding me? All the time they crash into walls. 2013. I don't think a turtle. So it is actually okay. Let me just kind of come out. So what the mouse is doing right now, it is actually exploring. But as it is exploring, it's adding the newly discovered walls into the map. And every time the map updates, it is recomputing the shortest path to the destination. And so all of this is being done in real time. The destination is the single peg in the middle, right here. So the mouse is actually trying to get there. And you will see the mouse is not even going to bother with all the cells on the other side, because none of the cells on the other side would be a part of the shorter path. So it's really trying its best to get to the destination as quickly as possible. This is more of a typical mouse. It's a stepper motor type of mouse, and it's slower. Okay, it's definitely not as slick as the other one, and it just kind of almost bumped into a wall. Thanks to error correction, it is actually avoiding that. It's not stopping. That is that represents a pretty typical first generation micro mouse from the United States. You haven't seen the Singaporean or the Korean type. Yeah. You need a pretty good frame rate to capture those. So yeah, that's kind of iffy. Okay, so anyway, this is the kind of competition that people, basically senior year engineering students would enter. I used to teach that class at UC Davis, so I know. I used to teach that class. It's a let's see, 322. It's a 7-unit class distributed over 3 quarters, which is 1 academic year. You have teams of up to 5 students, and It just fast forward because it's so slow and boring. And you have teams of up to 5 people, up to 1 year to work on a robot like this one. They used to have micro mouse competitions on Picnic Day, which is the open day of UC Davis, which just happened, what, 2 weeks ago? But they don't do that anymore because they lost the funding. They did not have enough money to keep me on as an adjunct faculty over there. So, after I stopped teaching classes over there, nobody picked it up. And I did not turn on the audio. Right about now, there will be like a roar of applause, because it is not common that a micro mouse would actually solve the maze in a competition. A lot of times they run into walls and stuff like that. All right. So,
Fast one.
well, this one is more continuous. Okay, it's more continuous. It's exploring, but I can tell right now it is not using the flood fill algorithm. This one is using what we call a depth first search algorithm. In other words, it will keep going until it hits a dead end, then it will back up to the last point where there's an alternative path, and it will go to another dead end and then back up. It's not gonna work. Just from experience, I can tell you depth first search is not gonna work because they would go to a lot of cells that is unnecessary to explore. So anyway, I try to teach this kind of class here at AR, but because I cannot tie that class to a transfer degree, I cannot get people to enroll in a class like that. But it will be a fun class. It will be a fun thing to do.
Make it part of the last part of this class.
Yep. Okay, but looking at these videos, okay, do you have time to sit down and go like, well, let me kind of think for 5 seconds to determine what I should do next? You don't, right? So with a flood fill algorithm or a modified Dijkstras algorithm, what type of processing power are we talking about here? Are we talking about a, I don't know, ARM type of processor, like a cell phone processor to do something like this?
Probably an Arduino.
Arduino, okay, you are right on the money. An Arduino type processor would be able to do it. A 16 megahertz processor, 8-bit processor, okay? So think about this, 16 megahertz, 8-bit processor with about, I would say 64 kilobytes of storage for program and about 2 kilobytes of storage for variables and arrays and whatnot, and the stack is gonna be able to do this. I actually computed how much time it would take to finish one round of the flood fill algorithm. It's about 20 milliseconds, even with a 16 megahertz 8-bit processor. Yep.
And how long do you think that would take, like an i7 in the newer desktops today?
Well, you're talking about an order of magnitude that is about. Well, okay. Let's just figure out the numbers, okay? So you're looking at 16 megahertz as opposed to 3 gigahertz. I know you guys overclock your stuff, okay? I know you guys overclock your processors, but 3 is a conservative, estimate, right? You're talking about an 8-bit processor here, and this is at least a 32-bit processor, okay? Okay. In terms of the number of ALUs, this one has 1 single ALU, and this one has got, who knows, at least a dual core, and then each core has at least 2 ALUs. So we are talking about 4 ALUs over here. So if you multiply the differences here, 16, let's call this 3.2 just so it's easier to calculate. So this is 32,000 versus 16, so it's off by what?
Factor
200?
Yeah.
Looks like 200 to me. This one is off by 4. This one's off by 4. So this is the most conservative estimate of performance difference. So we are talking about 16 times 200, which is about 3,000 times. Okay, that's conservative. Yeah. So if one takes 20 milliseconds, the other one will take 20 milliseconds divided by 3,200.
So about a half a mil, or not even a half a mil.
Hundreds of microseconds. Yep.
So what do they use in Singapore? Because I've seen their high school competition, and it's way faster. Like it doesn't get avoid half of the stuff.
Well, I think the one that you have seen may not be a high school. That might have been an open class. Yeah, well, that's because they emphasize a lot on science, engineering, and math. Does it bump into a wall?
No, it was that.
He was in one
It
tower.
came out.
Well, this one is using the flood fill algorithm, which is the one that I talked about, because it's constantly trying to use the shorter path or what would be the easier path to get to the destination. I can actually tell which algorithm it's using after teaching that class for so many years. Once a mouse start to roll around in a maze, I can actually tell what type of algorithm it's using. All right. Well, if you guys are interested in something like this, we can kind of talk about it after class and see if we can start a little micro mouse club here.
Have you ever seen any really creative ones, like maybe ones that like hop over walls or something?
You can hop over the walls. I mean, there's no rule to say that you cannot. But I have not seen anyone like that one because it's not necessary because after you have seen the fastest mice, there's no need to do it.
Because if you know how far you are generally, and like if you start at a corner, probably like triangulate the middle.
Yeah, it would appear to me that UCLA is now the dominant school in micro mice. UC Davis had the longest winning streak in IEEE Region 6 history in micro mouse competitions. The second strongest school was the University of Hawaii. And they would actually, every year, there will be like 6 teams, and each team has like 8 or 9 people because they have family and stuff coming to California. So I think they're just using it as an excuse to get out of the island. So anyway, but that's one application of the search algorithm, or at least a modified version of Dijkstras algorithm. Okay. So I'm gonna stop this one here. I know it's entertaining, much more entertaining than looking at this stuff here. Okay. Okay, so the next one, talks about the A-star algorithm, which is also linked to a Wikipedia page. So for those of you who want to know the details of the A-star algorithm, this is what it is. Now, the A-star algorithm is a little bit different from Dijkstras algorithm in that it makes use of what we call a heuristic. Okay? A heuristic function is basically a function that maps a vertex to a real number, which is quote-unquote an estimated distance to the destination. Okay? It's not a true distance, okay? It is just an estimation. So when you look at a maze, okay, like a maze that we just saw earlier, okay, so we'll just make a picture of a maze here. Okay. So let's say your mouse is physically over here, and this is your goal, your destination, okay? And there are walls configured, kind of in different ways in between, okay? So if you just need a quick way to compute, okay, I just need to get a rough idea of how this particular position compares to this position here, what you can do is just to calculate the straight distance between this point and the other point. That's a quick calculation, doesn't take a whole lot of computation power. Is it accurate? Probably not, because it depends a lot on how the walls are configured. But this is a heuristic. So if you can come up with a heuristic that is also guaranteed to be an underestimate of the actual distance, then you can use the A-star search algorithm. The A-star search algorithm is kind of like Dijkstras algorithm, but it makes use of heuristics. In other words, it makes use of heuristics to basically say, oh, I can see that if I go any further on this side, it's not going to be helpful because the heuristic on this particular vertex is already quite expensive compared to my other alternatives. So I'm going to explore the other alternatives first, okay? And that's the A-star algorithm. It is more complex compared to Dijkstra's algorithm because you can revisit a particular vertex twice or more than that, just because of the way the heuristic is set up. You can also look at Dijkstra's algorithm as a special case of A-star where the heuristic function returns 0 all the time. In other words, there's no heuristic function, it is only returning 0 all the time. Are we doing okay so far with the general concept? Yep.
So if that maze of yours had a left side, it wouldn't even bother with it, right?
That is correct. That's the whole point of the heuristic function, because if you look at this cell, this particular vertex here, because if we are sitting here and we have alternatives to go here or here or here, and you use the heuristic to guide you, then you will basically say, I'm not going to go here, I'm not going to go here, because the heuristic is saying that it's more expensive to go here, and then to the destination than these two other cells. Or at least it will prioritize and say that you should explore these two first because they are more likely to get you to the destination. Now, on the other hand, it is possible that this one, these are all dead ends. Okay, so it will force you back to explore the other two cells, as alternatives, because eventually you will find out these two are dead ends. But it helps you prioritize, which way should I explore or consider first. Yep.
Depending on how these sets of maze, though, depending what algorithm you use to explore the maze, you can actually be lucky in that your algorithm optimizes for that maze.
I'm glad you brought that up, because every single year there will be at least a few mice that are completely done by electrical engineers, and you will see the best machine job, the best components, and then from the software perspective, I call those dumb luck mice. Okay, because they really have no real algorithm to determine which way to go. It's somewhat random, and it's just by luck that they might run into the destination. But getting back to your question, which was, gosh, I forgot already.
Oh, yeah. Depending on how the maze is set up, the algorithm could be
Yes.
optimized or not optimized.
Yes, that is absolutely true. So with the Flufffield algorithm, I personally, every year I design a maze that will quote unquote defeat the Flufffield algorithm. In other words, the design of the maze will force the robot to explore a whole lot of regions in the maze instead of getting to the destination just like that. But the point about the Flufffield algorithm is it is still better than the alternatives. But you can design mazes to make it go explore more portions of the maze before it finds the shortest path. But it will find the shortest path, relatively quickly. It's still your best bet, basically. That's the whole idea. Are there any questions about the A-star algorithm? No questions? Okay. So we are basically just kind of exploring these names here, and the basic major difference between Dijkstras algorithm and the A-star algorithm is the use of a heuristic function. It's basically an underestimate of how much more, what is the distance from a particular vertex to a destination. Are we still doing okay so far with the algorithms? Okay. So here we get to this part here. One potential problem with both Dijkstras algorithm and the A-star algorithm is they cannot give you a partial answer. Okay, and the problem of not giving you a partial answer is what if your graph is really, really big and you have a real-time requirement. In other words, this is in a robotic application where you do have to do something before a certain time is up. Okay. Dijkstras algorithm, before it completes, cannot give you any recommendation. It will just say processing. Okay, I don't have a recommendation for you. The A-star algorithm is the same way. Okay, in fact, you can craft a heuristic so the A-star would actually take more time to complete compared to Dijkstras algorithm, which does not use a heuristic. You can make a heuristic function that is actually misleading, so it would actually take more time. So what if you have a robotic application where real-time performance is a key factor, and you cannot wait and say, oh, okay, this is going to finish in 5 minutes, but I have to do something in 20 milliseconds. Okay, so how do I get at least an idea of what to do within 20 milliseconds? There's a search algorithm called the C-star algorithm. Unfortunately, I cannot find a reference to the C-star algorithm on the internet, which is really funny because this is what I use as the basis of my dissertation, and and I was pretty sure that I was able to find literature, in terms of books, back in those days, and on the internet I could not find any references to the C-star algorithm. But anyway, it's a recursive algorithm. Okay, this is, to my best knowledge, this is how much I can recollect. So short of driving to Davis and going to science and engineering library to take up my own dissertation and read it, this is the best I can do at this point, okay? It's a recursive algorithm. It's relatively simple. It does not keep track of complicated data structures. And yet, it can give you a recommendation, okay? So what it does is do something like this, okay? So if I just want to use a graph or want to use a picture to represent what it's doing. So if you consider a graph, it can be really huge, okay? So this is, let's say this is the entire graph, okay? This is your starting point, and let's say your destination is here, okay? So this is your initial state, this is your goal state. So with both Vstar and Dijkstras algorithm, it really needs to find the exact path to go from the initial state to the goal state. Okay? And before it finishes the algorithm, it cannot give you any recommendation. It does not even want to tell you anything about what it knows up to this point. The C-star algorithm is recursive, and it is also successive. So by changing depth, which is represented by the variable d here, you can say, okay, I really don't know how much time I have. So I will set d to 0 first. So what it will do is it will only explore the immediate neighbors of the initial state, and then use the heuristic function of each one to figure out which way may be the best way to do it. Are we doing okay so far? So these lines are all based on heuristic function. These are the actual cost. F is represented the cost function. So we use the actual cost to go from the initial state to the neighboring state. But from each neighboring state to the final state, we use h to estimate what is the actual cost. Okay, which obviously is not going to be very accurate. But based on how much time we have, this is this may be the only thing we can do. Okay, so let's say after we run C-star with 0 as a depth, and we still have time. Okay, then you increase the depth to 1. What that will do is it is going to increase the depth of exploration, so that now you will start to explore the second layer of nodes. So you will go here, here, and you can even have the circles here or cycles. It doesn't really matter. So then you will explore not only the first tier but also the second tier vertices, and then the estimates will now be more accurate because we are now actually exploring the cost of 2 vertices or 2 edges and leave the rest to just the heuristic. Okay. If you have time left, then what you do is you increase the depth yet to another number, and you keep increasing the depth until you run out of time. So based on the last time the C-star algorithm is coming back and give you a recommendation, at least you have something to do. Okay, there's one recommendation. It may not be well informed, okay, because you can only go so far, but at least it will give you an answer. So that's the C-star algorithm. It's simple to implement. It is not entirely optimal, okay, but it is not designed to return an optimal answer because we have Dijkstras algorithm and the A-star algorithm for that purpose already. This one intentionally is going to give you an educated guess of what would be the good next move. Are we still doing okay so far, just in terms of general idea of how these algorithms differ? Yep.
So if you have a lot of processing power for these algorithms, would be better than other ones?
I can tell you one thing that this one is really good for is when you have parallel processing. Because of the recursive nature, anything that is quote-unquote recursive, a lot of times it will lend itself to parallel processing. A-star is not easy. A-star is not easy to parallelize because we have the shared data structures. So all of the threads that are actually going on at the same time, sometimes you have to lock up one because it's waiting for something from the other one. But C-star being completely recursive, you can just spin up a new thread and say, oh, this core is going to handle that new thread, and it will go in parallel to the other ones. So you're absolutely right about that part. So C-star, because of the simple nature and it doesn't need to maintain a lot of complicated data structure, it makes it easier to make it so that it will it makes use of parallelized hardware. So are there any questions about these three algorithms? Dijkstras algorithm, which does not make use of heuristics. A*, which is kind of like Dijkstras, but it makes use of heuristics. And then C*, which makes use of heuristic functions, a heuristic function, but it is kind of recursive, and this is what I call a successive estimating, recursive successive estimating algorithm, because that's the nature of this thing. It also has some, optimization in it too. So if you think about this particular instance, okay, let me just use a green pen here and a blue one to indicate, what I'm going to illustrate. So let's just say that you go from here to here and to here, and from here you use the heuristic to measure the actual distance. So let's say the blue path is giving you a estimated cost of, I'll just use a real number here, okay, 45 units. I don't know what unit it is, but it's 45, okay? And then you go to the other node here, which is this one here. But if this, okay, so if you go back to this node here, and you go to from this node to this node here, and the cost here plus the heuristic, if this is already more than 45, you don't even need to bother to look at these two nodes. Am I making any sense? In other words, you can use the best known solution, even though it's using a heuristic, to set a new boundary and say if any new path is known to be costing more than this much, don't even bother to go to explore those, because I think we have a better way to do it already. So that's kind of like a pruning technique here. You can basically say certain nodes do not need to be explored or expanded. The C* algorithm takes care of that using the conditions that is already set up here. C is the cost up to this point, up to this particular vertex. Fbn is the cost of the edge going from B to n. And then Hn is the heuristic function applied to n, which is the estimated distance from n to the destination. So if this is less than B, which is the boundary, which is the bound, then you want to do some exploration. But if this is already more than B, that means we already know a better path to do it. So don't even bother to expand on this node. Yep.
Can you like mix and match? Like, can you maybe do every once in a while you do like a depth first run, just so that you if you have a midpoint you have a much better heuristic. Like wouldn't it improve your heuristics if you have
well,
once I go further out?
The problem with the depth first is it will go in all directions, including the ones that do not make sense.
Gotcha.
So if you have a heuristic, you really should use the heuristic to help guide you and prioritize what you should expand. So last but not least is the depth first search algorithm. This is another wiki page. And the depth first search algorithm is, some of you know that already, okay? Because what it does is it goes all the way, it goes all the way to a dead end, and it backs up to find a alternative that it has not explored yet. So in this case, this is it's not exactly a binary search tree, but it is a tree. So the order of depth first search is exactly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if you draw a picture, okay, I cannot really draw on the projector screen, but I can just kind of show you. It's called depth first because it will keep going until it hits a dead end. So it's not going to consider alternatives, okay? It does not consider alternatives until it meets a dead end and say, oh, bummer, I have to go back. So it goes from the 1, which is the origin, it goes to 2. It does not want to look at 7 or 8, okay, at that point. It just goes to 2 and say, give me one way to go forward. Okay, 2 has 2 ways to go forward. It will pick 1, which is 3 in this case. 3 has 2 ways to go forward. It will pick 1, which is 4. But by the time you get to 4, it is a dead end. Okay, it does not have any outgoing edges. Then what it does is what we call a backtrack mechanism. So from 4, it will back up to 3 and say, hey, at node 3, do we have any alternatives that we have not explored yet? And the answer is yes. Okay, node 3 has another outgoing edge to 5. You explore 5. 5 is a dead end. You go back to 3. But this time when you go back to 3, you have to remember that 4 and 5 are both explored. There are no unexplored alternatives at this point. So 3 basically effectively becomes a dead end itself. Then you back up to 2. When you back up to 2, you ask, okay, do we have any unexplored alternatives? But there's 1, which is 6. But after you explore 6, you go back to 2, and then at that point 2 has no open alternatives. Then you have to go back to 1. When you go back to 1, it has 2 open alternatives. One is 7, you go to 7. Once you explore 7, it is a dead end, you go back to 1, and so on. That is the depth first search algorithm. Okay? It is very simple to code. Okay, it's very simple to code. You do have to remember whether you have seen a node before, so that you know when you can meet a dead end or a cycle, so you can back up. The problem with depth first search in many cases is it does not do anything in an intelligent way. Okay, well, but breadth first search is kind of the same way too. Dijkstras algorithm does not make use of heuristic. In other words, it is not quote-unquote guided by a heuristic. So how can this be worse than breadth first search or Dijkstras algorithm? Well, Dijkstras algorithm will stop when it finds the destination. This one, well, this one is designed to traverse the entire tree. So let's say you say, okay, the algorithm can stop as soon as you find the goal. Okay? Dijkstras algorithm, using the cockroach example, may leave a good portion of the graph unexplored, okay, because it is just expanding its perimeter as much as not necessary to find the goal state that you're looking for. With depth first search, it is just going as far as possible on one side. Okay, so getting back to the Google Map example, okay, if I start off in the wrong direction, okay, remember the downtown map? Okay, so this is the downtown map, and I want to go from here to here. If I went off in the wrong direction, which is going to this side here, when do you think I will meet the dead end? When I see the Atlantic Ocean, right? So the depth first search will go, all the way until I see the Atlantic Ocean and go like, wow, okay. And then what do? I back up one step on the very pier that I look out to the Atlantic Ocean and go, well, I'm going to take the next alternative. And guess what? That's not going to be leading me back to here anytime soon. That is the problem of depth first search, because it is just not efficient. Okay? Now, if you think about the breadth first search algorithm, okay, it is not smart either. It will go in all directions, right? So it will first explore everything around here. So it will first explore everything around here, which is a small circle, and then it will do a bigger circle, and it is still not guided or intelligent in any way, because I should not even have explored the other side. But you know what? Before very long, it will find the destination. So it is still better than depth first search, because you won't go all the way. If I have to find one word to describe depth first search, it is an algorithm used by obsessive people. I'll keep going this way. I'm not going to go back up until I meet a dead end. The breadth first search algorithm is like, okay, this is not working out. I'm going to explore something else. It will just keep expanding the perimeter until it finds the destination. On the other hand, if you use Vstar, which is guided by heuristic, then this portion may not even be explored, because the heuristic says, hey, if you get to here, it's not going to help you get to here. So don't even explore, don't even bother to explore. Is that making any sense? Okay. And do you think this type of thing has anything to do with, I don't know, let's say the optimization of the use of registers in the compiler?
Sure.
How would that graph look like? Can it be represented by a graph? Okay, what are we talking about here? Okay, think about what a compiler has to do. The compiler has to look at your C++ code, okay, and figure out a sequence of instructions in order to implement whatever you need to do. So we'll just kind of focus on maybe a few, assignment statements and whatnot. Okay, so there are a few ways to do it. the compiler has a problem of, okay, what if you turn on optimization? In other words, you're telling the compiler to say, okay, give me the optimal instructions in order to implement these statements. Do you think that might have something to do with graphs or not? So in that case, what would the graph look like? What is one vertex and what is an edge? One edge would be an instruction in assembly or machine code. Okay? And each vertex is representing the outcome of executing a sequence of instructions up to that point. So your final states will represent what you actually want to be done, what you want to get done, and then the cost to go from the initial state, which is basically saying, okay, nothing is done at this point, there are no instructions executed, is the cost of a path, is the exact cost of a sequence of instructions to implement a particular statement in C++. Would the exploration of a shortest path in this graph be useful, be practical? Absolutely. Okay? And it's an optimization problem, and it is actually a difficult problem to solve. So with this out of the way, I'm going to kind of move on to the next one for 10 minutes or so. I think I should be able to get this done in 10 minutes. And this one has to do, it's basically using the mastermind game as a board game, as an example. Okay, how do we apply graph theory to mastermind, okay, in the game? So before we can talk about the mastermind game itself, let's go play a few rounds. Which is the whole point of, which is the reason why I choose this as an example, so I can play the game. No, that's just one of the reasons. Okay. Mastermind game.
There you go.
There you go. All right.
Oh,
So,
this game.
yeah, now you remember it?
Yes.
Okay. They even replicate the color of the plastic of the board game.
I see that, yeah.
Yeah. Okay. So what it's about is, in this case, the computer is the one that is generating a pattern that I have to guess. Okay. If I guess both the color and the position right, it will give me a score of a red peg. Okay. If I guess just the color right but the position wrong, it will give me a white peg. Is that okay? But the white peg and the red pegs do not indicate which peg that I guess is right. Okay, it would just say that one of the pegs of my guess is matching either both the color and the position of the hidden pattern, or just matching the color. Okay? Okay, so let's go ahead and start playing this game. And what we'll do is we'll allow duplicates. In other words, the hidden pattern can be red, red, blue, blue in this case. Okay, you can repeat the same color once. But as many times as it needs to. So a typical way to do this is, oh, I need to start a new game. Start new game, there we go. And we just
Start at the bottom.
the bottom. Yeah, there we go. So I just picked red, 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 check. Okay, so what this is telling me, because I'm getting a score of 2 red pegs, it's telling me that 2 of these 4 red pegs is both color and position right. In other words, it's just telling me that the hidden pattern has 2 red colors. Which 2? I have no idea at this point. Okay? So my next guess is to say, well, I really don't need to pick any 2 positions, for the red, but I know that there will be 2 other colors, or 2 pegs of colors other than red. So I'm going to use green here. Check. Okay. Things got a little worse than before, because this time I got 1 red and 1 white peg. But I know that both of those are due to the red pegs, right? So one of the red peg is already at the right position, the other one is not at the right position. I don't know which one is which, okay? So what I'll do, but the green ones are definitely wrong, okay? So I can remove the green ones and move on to the next color. So I will keep one of the red at one of the positions and put the other one here and do this one, check. Okay, so now we know there are 2 red ones and 1 blue ones. and then one of the other colors. Okay, so how do you pick the next pattern, the next guess?
Leave one of the blue ones in place, leave both the red ones in place, and change one of the blue's colors.
Okay, so this is
Sorry.
this is how. Well, yeah, no, that's fine. Let's go ahead. So let's evaluate whether this would be a good way to as a pattern. Okay. All right. So how do we evaluate whether this is even making sense or not? So what you do is you think about, okay, what if the hidden pattern is actually red, yellow, blue, red? Okay. Would it have given me the scores that I have gotten from my previous guesses? That is the evaluation criteria.
No.
So when you compare this to the previous one, it tells me right away and say, this doesn't make sense, Tag. Because if red, yellow, blue, red is the actual hidden pattern, it would not have given me the score that I got. It would have given me just one red tag because of this one, and then I would have gotten two white tags instead of one additional red and one white here. So this tells me this is not a good guess. Okay. So we have to keep two positions right. So what if we do something like this? Okay. So you have to compare to all of the previous guesses and make sure that it is consistent with all of the previous ones. Okay. So if red, blue, yellow, and red is the actual hidden pattern, the previous guess would have matched two tags completely. Would have given me the two red tags here as a score, and one white one because this one is color right because the position wrong. That's okay. What about the one before that? Okay, this will give me one red. This will give me one white, consistent. One red, two reds. It is not consistent. So it makes this one at least a valid, choice as a guess, as a new guess. Is it optimal? It's probably not optimal. In other words, if I want to play this game and say I'm going to use the least number of guesses to get to the actual pattern, this may not be the optimal way to do it. Yep.
Wouldn't the blue have to be in the third slot because below that, the two reds fit, so, but the blue is in white slot?
Okay, tell me what you want to do for this guess.
Like the blue in the third slot or the.
Okay, so blue goes here and the yellow goes here.
Yeah.
All right, so let's check. This would not be consistent with the previous guess because if this is the actual hidden pattern, then the previous guess would have given me just one red tag as a score and two white tags instead of what I got. Is that making any sense? Okay, if this is the actual hidden pattern, okay, and I guess, red, blue, red, blue, okay, this red would have contributed to one of the red tags, but what would the other red tag be coming from? Do you see what I mean? So that's how you can rule out possibilities. This is all about ruling out possibilities. Every single time you make a new guess, it will help you narrow down the remaining possibilities. So until your possibilities is narrowed down to a single one, then the game is not over. So we'll go back to the original pattern, which is one of the possibilities, right? So we say check. Oh, okay, so we got 3 right, but we still got 1 color wrong. But I know which one, I know I can lock down all 3 red ones at this point because I know the blue and the reds are right. It's just a matter of the yellow being some other color. And I have 4 additional colors to explore here. So now it becomes a pretty easy game. Just use brown here, check. That's how the game is played. The question is, how is this related to graphs, searching in a graph? And it looks like we may run out of time today to talk about it because Tech insists to play the game to its completion, which is now quite obvious.
It's white.
Yep. Yay.
Tell us.
Okay, but that's the game. That's the mastermind game. So now the question is, how is this related to graph searching, okay? And what are we really searching for? It's all written in the notes here, so you can just kind of read that part before next class. And then from there, we'll just kind of talk about, graph theory a little bit more, and then we'll move on to trees. Trees are easy, okay, because trees are a special case of a graph, so they're fairly easy to talk about. All right, we are running out of time today. I will see you guys on Thursday. And yes, I am grading the midterm. It's just that it takes a lot of time.
Is it Dijkstras search that you were talking about?
Vstar?
It's an incremental heuristic search algorithm.
So I remember the name from